Number 4 says this. A treasure map gives directions to the location of buried treasure. It begins at the entrance to an open field. The directions are 10 meters due north, 15 meters at 30 degrees east of north, 8 meters, 20 degrees west of north, and finally 12 meters south of west. That's got to be the 45 degrees. What is the direct route to the treasure? So, I want to start, as I suggested all of these things, with creating a coordinate system that will support this problem. All of this takes place in the first and second quadrant from what I just read. And I'm saying this because I'm just going to draw the vectors together real fast. You might not understand what I mean by that, so let's see if I can kind of prepare this for us. The first vector says to go 10 meters due north. Bless you. 10 meters due north. Second vector, 15 meters at 30 degrees east of north. 15, so it's got to be longer than that, but 30 degrees east of north. That look good? Just kind of getting a rough idea of what I'm going to do here. 8 meters, 20 degrees west of north. 8 meters, 20 degrees west of north. And finally, 12 meters south of west. 12 meters, I gotta make it about a little less than that, 15, south of west. Now this is not to scale, just kind of estimate. It looks like it's a question mark. So you kind of see? This is kind of what we have. I see that there are 1, 2, 3, 4 individual vectors. We all good with that? All right. I know it gave everything in terms of north, south, east, and west, but for this activity, I'm going to make east the positive x direction. I'm going to make north the positive y direction, and west the negative x direction, and south the negative y direction. Right. Now, I'm applying the same coordinate system to every one of the vectors. But the first step for all the vector stuff has always been apply a coordinate system to your problem. I've done it now. This will be the coordinate system I will use for each vector in the problem. We all good? I've been doing this the other times too, but we've only had 1 or 2 vectors. There were 4. Put that off to the side. I'm going to make myself a little chart with 1, 2, 3, 4. Step 1, convert from polar to rectangular. So my polar, I have 10 meters north. I have 15 meters 30 degrees east of north. I have 8 meters 20 degrees west of north, and I have 12 meters 45 degrees south of west. These are my vectors. We all good? I will take those. I'm going to add them up, but to do that, first I have to convert each of them to rectangular. I'm setting up a grid. Kind of writing a chart out here. This whole chart is a statement that says convert from polar to rectangular. But there's lots of little things that go along with that, and I'm not going to give you the baby steps, right? You're better than that. Now, I have to do each one of these, but I'm not going to have to really draw out the first one. The first one is just that, right? Because it's all positive y direction. Now, for each of these other ones, I'm probably going to have to do something more, aren't I? Pretty sure. So let's start with number 2. Number 2 looks to be all the way in the first quadrant. So I'm going to just kind of make a first quadrant for this. Is that it? I'm drawing 15 meters, 30 degrees east of north. That looks like to you guys? So the conversion part requires that I use a different set of steps. And this is converting to my component vectors. So that's what I'm doing right now. I'm going to convert to my component vectors by drawing in a triangle. And I'm wrapping that triangle around the given angle so that I can identify the angle of focus and label the opposite and adjacent side. And after this one, I won't do this again. But I will say sine of 30 equals opposite over hypotenuse. Cosine of 30 equals adjacent over hypotenuse. So opposite equals 15 sine 30, and adjacent equals 15 cosine 30. From now on, I'm not doing the trig like that. I'm just going to list out the trig, okay? You guys should be progressing because you've practiced. All right, going to keep going. 15 sine 30 is just 7.5. 15 cosine 30, 12 point something, 12.9. Okay. Great. I'm noticing that the adjacent is in the positive y direction and the opposite is in the positive x direction. So I'm going to go ahead and write that in. In the x direction, I am going out 7.5. And in the y direction, I'm going out 12.9. We good? All righty, still going. All right, so the next one was, can't read it, so there. 8 meters, 20 degrees west of north. So I'll start by, this is 8, this is 20. I'm gonna put in my, components. I'm gonna have a component like that, and a component like that. That's the triangle I'm choosing to do. Good? All right, good. This one's going to be 8 sine 20. This one's going to be 8 cosine 20. I think I'm at a point where I can start doing that now. I feel pretty confident in my trig skills. Some of you must feel super confident. Very excited to see that confidence. I'm going to break this down now into the component amounts. I should be able to call on just about anybody. Somebody has spare time. I'd get a calculator out if I were you. You're going to be the first person I'm going to ask to help me out with stuff. So 8 times sine of 20 looks to be 2.736 blah, blah, blah. Somebody's bound to ask how many decimal places. Right now, you should keep all of it. Right? It's an intermediate step. At the end, I'm going to want it whatever number of significant places I have there. But when you're in a mid-step, you should keep lots of decimal places. And I would include in your chart. I'd use more than this. Now, I'm going to do both of them real quick. So I've got that for that. Was that good? You guys do your trig all right? Be careful here. In this case, the horizontal component points in the negative x direction. So I got to make sure when I'm writing these into my chart here that this is negative 2.736. This is 7.518. We good? All right. Got one more. That's going to be number 4. And that guy is 12 meters, 45 degrees south of west. That clearly puts him in the third quadrant. It's 45 degrees, and although it says south of west, it doesn't really matter. We know about 45 degrees, so I'm not too worried. But I'm going to put my 45 degrees here. I'm going to list out my components, but I'm doing this mostly for the kids who are still struggling a little bit to make sure you understand that, this is what you're doing. Still the same stuff. The difference is mistakes made here won't show up as much. This is still going to be, it's 12 units long, so this will be 12 sine 45. This will be 12 cosine 45. And 12 times 45 sine. I get 8.485 something something. So that's both of these, 8.485, 8.485. And I'll put out that they're both in the negative direction. All right, we have converted all of our vectors from polar to rectangular. Step 1 complete. Step 2, add together like components. So, add. All right, that's all you have to do. So, Lynn, what are the x ones? I'd like the x ones, please. Can you add them? We agreed? Excellent. Excellent. So, somebody else give me the y's. Let me see. You guys still tapping? Or you got it, Leah? What is it?
1.93.
What was it? I couldn't hear you.
21.93.
Okay, 21.93. Thank you. Is that all right? Leah, do a good job there? All right. We add up like components. This is in the x direction. This is in the y direction. I don't think it's too much for you guys to recognize I'm adding a little bit here and there. This is vector notation. It's okay to write a vector like this. I'm telling you that this is 3.72 in the negative x direction, which can't be added to 21.93 because it's in the y direction. So this is a complete statement, like an ordered pair. So it's no different. They're both in terms of meters because these were all displacement vectors. But the last step is to convert back to polar. So my last step, go back to my still my original coordinate system. Based on what I'm seeing there, I'm going to be in the second quadrant, I think. And my components tell me to go upwards 21.93. And over 3.72. Clearly not drawing the scale, but now there's still a few of you in the room who think that the best way to do this is to do that. That's not true. Remember, when you get here, you add tip to tail. You make a triangle, and you start by deciding that you're going to do either this or that. Does not matter which one of these you do, but this is how you get the direction correct. You'll get the hypotenuse length fine, but your direction will be wrong if you do it any other way. So I'm going to stick with this one. Now, I know that all of you can figure this out here because, you all had the Pythagorean theorem. That was the one thing you could all do if it comes to a triangle. There's still a few of you having to work to get this. It's not much work. I'm looking at this and noticing that's the opposite, that's the adjacent, that's the hypotenuse. So tangent of my unknown angle equals 3.72 divided by 21.93. So you get 9.6 degrees. This is not the answer. To get the answer, I'll still need the length of the hypotenuse, which you got from Pythagoras, which I think is like to 23. Is it more? 23 point something? Or 22.2? Alrighty. So the answer would be 22.2 meters, 9.6 degrees west of north. lots of chances to make mistakes here by little mistakes, right? Yes, ma'am.
Why did you just get rid of the negative? Is it only there when you're plotting it?
The negative tells you the direction.
Yeah.
So in the case of, if you're talking about this one here, this vector, that negative told me whether I was supposed to go this way or that way. But once it's there, I don't need that negative any longer, right? I am dealing with the direction directly. If you put the negative in there, you'd be making your tangent negative. Now, there's reason to do that. The tangent is negative in second quadrant. But I'd be careful about relying on that to help you deal with direction. I would deal with direction directly by looking at something that you will provide for reference and then making your reference work for you. Like I know that this angle, 9.6, I know exactly where it's relative to because I chose the triangle and I made reference to that from the very beginning. If you don't do it that way and you put the coordinates in just positive and negative, you have to interpret because how would you know if it was supposed to be in the second quadrant or the fourth quadrant as tangent is negative in both of those? Does that make sense? I find it easier just to draw it out. And my experience has been most students recognize that too. But remember, negative in this class when it comes to vectors is only about direction. I think it's your job to interpret that direction and provide an outcome from that. All right. So that was number 4. I will do number 5. A plane is attempting to land on a runway that is due west. The wind is blowing at 25 meters per second at an angle of 30 degrees north of east. The plane has to maintain airspeed of 100 meters per second to land successfully. What direction should the plane face while landing, and what will its ground speed be as it lands? Alrighty. This sounds terribly familiar. Like maybe we did this one like this. So I hope that this works out. The plane has to land due west. So I'm interpreting that as the plane having to go that direction to land. And I'll make this west. All good? Step 1, I'm going to put together a coordinate system that I feel appeals to this problem. That will require me to draw in coordinates. So doesn't matter where on the runway you draw the coordinates. Somebody asked that in one of the other classes yesterday. I don't know which one. I'm just providing reference, just a picture. And for this problem, I'm going to make the positive, this the positive y direction, this the negative x direction, this the positive x direction, and this the negative y direction. But we're still talking north, west, east, and south. All good? All right. Let's talk about the 2 vectors real quick. They are velocity vectors. So the first one I'm going to talk about is the wind. The wind is blowing at 25 meters per second at an angle of 30 degrees north of east. That's what I see for the wind. 25 meters per second, 30 degrees north of east. We all good with that? All right. In order for the plane to land only going due west, so I want the resultant vector to be due west, I think the plane is probably going to have to point itself like that way. Does that make sense? I need the y components of the velocity to cancel out, the north-south components of velocity to cancel out, so that the plane's only ground speed, its only ground relative velocity is east to west. So I don't know what angle this is going to be. I'll list it as theta, but this is 100 meters per second. Step 1, convert all of my vectors from polar to rectangular. So I have the wind, and I have the plane. The wind is 25 meters per second at an angle of 30 degrees north of east. And the plane is 100 meters per second, and it's going to be something south of west. But I don't know how much. All good? just move that over a little bit. I'm going to list this as x, and this is y. We're going to convert these suckers first. I left the wind visible so that I can kind of draw on it right there, if you don't mind. I'm going to put a component like that, and another component like this. I am going to list this as my adjacent side, this is my opposite side. So I see the opposite as 25 sine 30, and the adjacent as 25 cosine 30. All good? It looks like the opposite side is going to be in the positive y direction, so that's going to be 12.5 in the positive y direction. The other one is in the negative x direction, so negative and 25 cosine 30, I don't know what that is, 25 times 30 cosine. 21.65. All good? All right. The plane, it's a little different because I don't have the angle, but I can still do all of these things we're talking about. I'm going to draw in my components. I'm going to label this the adjacent side and this the opposite side. Opposite side is going to go with the sine, so this is going to be 100 sine theta. And it's in the negative y direction. And this one is 100 cosine theta, and it's in the positive x direction. So 100 cosine theta minus 100 sine theta. I've converted all of my vectors from polar to rectangular. Any question about that? Okay. Again, back me up. I'm doing this problem as similarly to all the others as possible, giving you a framework on where to start, using our foundations to get our answers. All good? I'm going to add like components, but here is where I need to be thoughtful. I know something about our result. I said it at the beginning. Our result has to have no component in the y direction. I need the result to have a ground speed that is only in the x direction. That's how I'm going to solve this problem. I'm going to make sure that when I sum these vectors together, they equal 0. So 12.5 minus 100 sine theta equals 0. So 12.5 divided by 100. 7.2 degrees. Now, that's the answer to one of the questions. So let's handle that first. This angle here, theta, is 7.2 degrees, but the plane's heading is 7.2 degrees south of west. Well, I guess I should put that all inside there. Whoop, I'll do that. 7.2 degrees south of west. The plane is actually traveling at 100 meters per second, 7.2 degrees south of west. But that's not the ground speed. That's the speed of the plane relative to the air. The ground speed is going to be whatever this result is, which looks to be 100 cosine 7.2 degrees minus 21.65. This will be the ground speed. So 77.6 meters per second. Projectile is. A projectile is an object that travels in 2 dimensions but experiences an acceleration in only 1. That's the definition of a projectile. It's a bold-faced lie, too, and I'll explain that in a minute as well. But I would still like you to write it down for those of you who take notes, because I think you'll find it important in a few minutes. Again, a projectile is an object that travels in 2 dimensions but experiences an acceleration in only 1. Do I need to repeat that a third time? Excellent. A projectile is an object that travels in 2 dimensions, but experiences an acceleration in only one. There are no real projectiles except in places where there is no fluid present, no atmosphere. But you throw any object, it is a projectile. Real projectiles have more complicated trajectories. Now, if you don't know what these words mean, let me help you out. A projectile is the object that is thrown. I think that's obvious. The word trajectory has a specific meaning that you should know. It is the path that the object takes from launch to landing, the physical path. In fact, a trajectory equation tells you X, Y, and Z for every moment of the object's motion. It's a trajectory, it's a path. You can plot a trajectory in a 3D map and you'll see a line going through the 3D map of the object's pathway through space. That's what a trajectory is. It doesn't tell you when it was at any of those places. It just tells you the path that it took. That's what a trajectory is. Now again, I want to be very clear. An actual particle's trajectory is complicated because there's all sorts of things pushing the object around because it travels through a fluid. There's air resistance. There's the fact that the object might be spinning and therefore causing changes in pressure on either side of the object. Watch baseball, watch basketball, watch football, watch what that ball does. Because the balls are designed to grab the air. Look at a golf ball. Believe it or not, they've had to now regulate the dimple pattern on golf balls because with enough manipulation, you can make golf balls go farther. So several golf ball dimple patterns have been banned by the PGA because they give players an unfair advantage. Because they can hold on to the air more and make the ball go farther. So the idea that what we're going to describe today is what's really happening is false. Because there's air. And air mixes this all up. Now, in about a month, we'll bring this back. And we'll do some real problems that involve air resistance. But for the time being, we're going to assume that our objects are not experiencing any air resistance, and therefore our projectiles are pretty simple. So let's set up a straightforward projectile idea. A projectile begins when an object is launched at some angle. So let's get our projectile launched at some angle. Doesn't really matter what we're talking about. We're talking about some object being launched at an angle. I'm making this big and out of proportion, but I think you guys are pretty aware of what's going to happen here. The object is launched with some initial velocity. I'm introducing you to the symbology I'm going to use. The symbology is not standard. It's just what I'm going to use for this class. So the launch velocity is V0. It generally includes an angle to tell you the launch velocity's direction with respect to something else. For projectiles, the thing you want to know is we generally use the horizontal as our reference direction for a projectile. So it's not uncommon to label the horizontal as the positive x direction for a projectile, which will mean that we will have we'll have a y direction as well. So the launch velocity generally comes with an angle, and we measure that angle almost always relative to the horizon or the horizontal. Those words are interchangeable. So if I say it was launched at 20 degrees with the horizontal, I'm saying it was launched at 20 degrees relative to an x-axis drawn parallel to the ground. Is that good for you guys? I'm being as specific as possible so you understand all the nuance. Now, I don't think this part is a surprise, but the projectile is going to have a path that looks something like this. I'm not saying it's parabolic, but in a day or two we'll prove that it's parabolic. So the trajectory of a projectile is a parabolic path. It's a fun sentence to say. Bring it up at dinner tonight. It's got a lot of big words in it, and you'll know the definitions, but they won't. Right? Trajectory of a projectile is parabolic. It just makes you sound nerdy saying it. Some of you know what it means, and that's good. I want you to consider that the important detail here is that this object, as it travels through the atmosphere, is experiencing a single acceleration, the acceleration due to gravity downwards. So this object fits the requirement of a projectile. It's traveling in 2 dimensions, but experiencing an acceleration in only 1 dimension. Now here's the real thing about projectiles, the most important thing I'm going to say about them today. Real projectiles are kinematics problems that can be separated into 2 one-dimensional problems. Let's say that again. Real projectiles, because they can have accelerations in both directions. I want to be very clear about it. Real projectiles can. Real projectile problems are problems that are 2-dimensional, but can be broken up into 2 one-dimensional problems. You only have 1-dimensional math. So, the first thing I want to make sure you see here is that our object has 2 components related to its launch velocity. The first is a horizontal velocity, which I will label Vx. Vx is traveling in a horizontal direction, therefore it is not experiencing any acceleration. At the same time, at launch, the object experiences a vertical velocity. The vertical velocity I'm going to list as Vy initial. I'm putting the initial symbol there, not just to designate that it's in the y direction. We already kind of cleared that up. But the 0 there is to remind you that it will be experiencing an acceleration. So it will only have this velocity at the moment of launch, but it will maintain this velocity the entire time it is moving. Let me say that again, and I'm going to say it in very specific language. The y velocity experiences an acceleration and will continuously change throughout the object's path of motion. The y velocity is experiencing an acceleration, and it will continuously change throughout the path of the object's motion. The x velocity is a constant. It will stay the same from launch to landing. In fact, consider that the object can be in several places. No matter which of these places we look at, the object's horizontal velocity will always be the same. But the object's vertical velocity will always be changing. All right? That's a projectile. All right,